we'll have plenty of people joining as we move along, but we're going to go ahead and get moving forward now. Real quickly, I want to thank everyone who has joined and who has bared with us during the process of our meeting last week and this week's meeting. We had some technical difficulties with our provider. We had switched providers and rescheduled, and now we still have the same overwhelming response to this webinar. We had about 200 people who have registered for the event, and which is really a great turnout. So thank you again for taking the time to be here. Real quick, my name is Bobby Hambrick. I'm the CEO and co-founder of AutonomouStuff. We have a global distribution contract with Viz Lab, and for those of you who are not familiar with AutonomouStuff, I'll tell you a little bit about us, and then we'll get started with Alberto presenting the main topic today. So at AutonomouStuff, we work really hard at bringing together the world's best technologies, and we're known throughout the world as a leader in providing components to help enable sensors that help enable autonomy systems. We really have three main business segments. One of that is our core product offering, being laser scanners and radars, and of course stereo vision and other components used to help enable autonomy. And also our services group, which consists of an engineering team, which is a very strong team of application engineers that help support our products, and also a knowledge-based services group. Our knowledge-based services group is very passionate about transferring knowledge based on actual experiences, and then we're now traveling the world providing workshops, keynotes, and general consulting. We like to start with this service by just providing a one-day state-of-the-industry update workshop. So again, we've had an overwhelming response of over 200. We're going to have everyone on mute until the very end, and once we reach the end of the presentation, and if you have any additional questions, then please press the little hand icon or raise the question, and then we'll take a look at that. We'll unmute you, and then we'll have an open discussion at the end of the event. I would like to introduce also that we're going to be providing very special discounts for the attendees who attended this event. We'll provide a 15% discount on all plug-in modules that go with the stereo camera hardware, and that includes terrain mapping and obstacle detection. Alberto will be providing all those details on what that means during the webinar today. Now to introduce Viz Lab. Viz Lab is an acronym for Artificial Vision and Intelligent Systems Lab. They're known for their applied research on environmental research, and this is based on many years, and Alberto, I'm sure, will cover more details of that. And now for the main event, an introduction to Alberto. He's a full-time professor at the University of Parma. He's also the president and CEO of Viz Lab. And Alberto is a pioneer in the use of machine vision for automotive applications, and in addition with driverless cars. He has been involved and authored more than 150 publications, and is included in several book chapters, and has been traveling the world telling his story. He's a great person, and we're very proud to have him with us today. And if you like, Alberto, you can go ahead and take over and get started.
Sure. Can you hear me now? Okay. So, well, good morning to everyone. I'm very happy to have the possibility of presenting our technology. We've been working on this for a number of years, and I'm very proud to be able to share now with you and with the world, and help people that are willing to do some research and applied research on artificial vision with this new device. Together with me today, I have Paolo Zani, who will be running the second part of this presentation. I will be covering mainly the most important aspects to present our 3D system, while Paolo will go more deeply into some more details about the system and how you can use it and how you can configure the system. I will be starting by just showing a few video clips that actually summarizes our history. We have been working on autonomous vehicles for 20 years now. We have been dealing with different vehicles and different scenarios. So it's thanks to this background that we developed some knowledge on perception for vehicles. And what I'm presenting today is a kind of result of our history and our research in the last 20 years. As you can see from the video clips, we started in 1994 with the first vehicle, which was actually fully manual. We had a project in 1998, the Argo project, that actually gave us visibility, global visibility, when we traveled throughout Italy with this passenger car. And then 2004, 5, and 7, we attended the DARPA challenges, so we had some experience with those vehicles. And so large vehicle in off-road environment and urban environment, well, simulated urban environment. And then 2010, we had our greatest challenge. We drove to China with the small electric vehicle that you see on the lower left of the slide. There were electric vehicles, and we developed the sensing system and the decision-making system and the control of the system. And on the lower right, you see the Brave vehicle and the test that we took last year in July, and where we drove in downtown Parma with no one behind the steering wheel. That was one of the first tests of downtown driving with nobody behind the steering wheel. Our focus has always been vision, and mainly stereo vision already 20 years ago. And now we have this system which actually has nice performance, and we would like to share this with the community. So what I mentioned already is that we developed this technology, and we would like to share with research centers and with our companies, so that in order to help them build on top of this. I would like to introduce you to the 3DV system, which is a stereo vision system, as I mentioned, it's made of a camera and a processing engine, and delivers a 3D world description out of it. So the camera is a normal stereo camera, and the processing engine can be any. We have our own solution now, which is PC based, but we are also looking into other possibilities and other solutions with that. We decided to develop this system and actually package this system because there was nothing else like this in the market. We have been also always working with cameras and processing for our projects, but this is the first time that we really take something from our projects and we pack it and we deliver it to someone else, so that those guys can build on top of this and continue the research, forgetting about the low-level part. So this is conceived to be an easy solution for people that really would like to focus on high-level. I just mentioned fusion, interpretation of the world, and navigation. What 3DV can provide, it's different things, starting from the raw images coming from the camera. If needed, they are also rectified. It can provide a disparity image, meaning that for every single pixel, besides color, you also have distance information. That the system can also provide terrain representation as a mesh, obstacle detection, and obstacle tracking. And we would be going into the details of every single item which is mentioned here, well, except for the raw images, of course. Other plugins, as we call them, are now being developed, and we will be adding new functions as time goes by. So maybe that in a few months we will have another one to be added to the current offer. And we are also developing some fusion boxes that can fuse information coming from 2 or more 3DV systems. So today I will just be focusing on one 3DV system with one stereo camera and one processing engine. But there's also an extension to handle more than one. Well, as I already mentioned, the 3DV system is a intelligent sensor that can be used by roboticists and engineers, field engineers in different fields. Today I will be talking about automotive environment, but we are also working on agricultural, defense, mining, and other different fields. And we have been applying this 3DV system into every single field that you can see listed on the screen. You will see now in the slide some examples of the application of this 3DV system in the automotive domain. You will see these video clips. Maybe they are a little choppy, but we also have on YouTube the smooth version that you can check. On the left-hand side, we have images captured during our trip to China, during the Parma-Shanghai trip in 2010. And in that video clip, you will see vehicle detection, tracking, and terrain estimation. On the right-hand side, you have an example of the very same system mounted very high on the vehicle, 4 meters high, and that's for large vehicles and tall vehicles, mining especially. And on the lower right, you will see the very same system mounted very low on the vehicle, so 50 centimeters from the ground, and that's used for robots, small rovers. In the next slide, you will see other video clips. On the left-hand side, still images coming from the Parma-Shanghai trip, and that's an example of off-road terrain mapping and obstacle detection all together. And this is kind of tricky because you need to understand that's an obstacle and it's not a bump on the road. On the right-hand side, still the same thing, off-road with the camera very high on the vehicle, so it's 4 meters on the vehicle. And on the lower right, it's a construction area. This is another application of our system used for construction vehicles. And in this case, you can see that the system can locate the objects and can even locate the negative obstacles, so the holes in the ground. That's another application. We are using that in off-road environments, and you will see this video clip shows a much denser mesh to represent the terrain in front of the vehicle. You will see, I'm not sure if you can appreciate that, but the mesh has different colors. Green is for flat and red is for slope, and it has all the gray levels in between, so all the shades between green and red. And you can safely and successfully locate the flat area which is in front of you where it's safe to move. Now I would like to go into more details about the 3DV system. And the 3DV system is a hardware system that allows you to start from the left image that you see in this slide and move on to the right-hand side. So we give a synthetic representation of the world, starting from the terrain approximation, and you will see in this case we have a flat area, green, and a slope, which is red. And you can also isolate the pixels belonging to objects, like the tree trunks in this image. So I will now start with some intermediate steps of the algorithm. Usually we start with a set of images coming from the cameras, so 2 cameras, stereo cameras, and we do the compute the disparity image based on a modified version of the SGM, which is a world-renowned algorithm for disparity. We have our own version with our own modifications to that. As you can see, it delivers a pretty dense disparity image, almost for every pixel we have a distance estimation. Once we have the disparity image, we take that and we analyze the 3D point cloud that the disparity image generates. And in this case, you will see a video clip that shows, again, maybe quite choppy, but I'm sure you will appreciate the density of the data, which is represented by the 3D point cloud. You will see this as a very dense point cloud, and you can move your virtual camera in different positions. Like, for example, now it's very low on the ground. You can zoom in into the objects, and you can pretty nicely understand that for every single object, we have so many 3D points. So detecting the objects, well, it's I don't want to say it's easy, but it's not that complex. And if you move your virtual camera low on the ground, you can also understand if the terrain in front of you is flat or it's rugged or it's coarse. So you can really understand very well the morphology of the terrain in front of you. Then once you have the 3D point cloud, and I already mentioned that it's a very dense 3D point cloud, once you have that, here's the tricky part. We label every single pixel as either belonging to an obstacle or belonging to the terrain. And this is very tricky because you need to have a definition of what an obstacle is. So if you think of an obstacle as something which is raising up suddenly from the road surface for a given amount of space, then you will be able to label every single pixel. You take just the terrain pixels and you use them to create a mesh. And in this other video clip, you will see that all the pixels belonging to the ground are used to create a mesh of the ground. And you can really see the bumps in the ground, the little hills, ditches, berms. And for example, now there's a ditch on the right-hand side, and it's pretty visible. Then actually you are keeping the very same obstacle pixels alone, and you will appreciate then that in this video clip you can see the terrain mapping together with the obstacles, the real obstacle points. Then the next step would be to create a representation from the obstacles, and we are using a kind of Stixels-like way to represent obstacles. It's not exactly Stixels because the way in which they are computed, and you will appreciate that, you will see that. We can also have floating Stixels, so objects that do not touch the ground, and they are also detected. And in this video clip, you will see on the left-hand side the 3D synthetic representation. On the right-hand side, it's a 2D representation of the world in front of the vehicle. And you will see the green area and all the objects which have different color based on the distance. So far away obstacles are yellow, and closed obstacles are red. Then the next step, I'm going through all the little steps, intermediate steps that are within the system. The next step is to group together different Stixels, and well, I'm using the word Stixel, but it's not correct. I mean different boxes, and create objects. Then every single object will be given an ID, and it will be tracked. So in this video clip, you will see a road scene with a flat area in front of us, and then all the vehicles are detected as a single object. Vehicles which are very close are grouped together. In this case, you're locating the car in front of us, and maybe you can also appreciate that on the right-hand side, you can still see the step of the pavement thanks to the very dense 3D point cloud that the 3D V is providing. So that's all for the very quick presentation of the 3D V system. I would like now to go more into the details of some of the usual problems of vision. So usually it's adverse conditions. So we tested our system during the 13,000 kilometers trip to Shanghai in 2010. So we developed that, we tested it, and then we continuously improved the system from 2010 up to now. So the system that we have now is much, much better than the system that we had in 2010. And we have been using all the data that we collected during this trip to improve the system, analyze the faults of the system, and try to improve them. We have been going through different extreme scenarios like dust and smoke, rain, light and heavy rain, snow, and even difficult scenarios like off-road, and even the whole of them together. And I would like to show you some performance of the system in those really extreme conditions. We tested that in rainy conditions. This is a video clip that shows the 3D reconstruction when there are raindrops in front of the lenses. And you will see that the system still locates the objects with some difficulty when it's far away, but still it can work even if the camera has some bad distortion. And remember that we're using a stereo vision, so we have two cameras, so maybe that on the other camera we have the same problem, so different raindrops in front of it. Other examples are snow. Well, this is an example which we acquired here in Parma. And I would like you to see how the system behaves in a very complex scenario when everything is white. So when everything is white and there is no texture, stereo vision doesn't work. But the system, the improved version that we developed, actually is able to work and provide a disparity, a very dense disparity image, as soon as some texture appears. So whenever you have a completely white area in front of you, well, nobody will be able to find texture and be able to work. But as soon as you do have a little texture, like the tracks of previous vehicles, well, that would be just enough to allow you to detect the distance through the disparity image. Another example of difficult situation is night driving. During night driving, we have some issues if the illumination is not enough. So you would appreciate in this video that obstacles are all detected, but the terrain mapping is not updated. So it's freezed because we don't have enough headlights power, and in this case we have very dim headlights. So the terrain mapping is not working, but obstacles which are illuminated, which have headlights, are detected. And this was a very extreme situation. Remember that all the videos that I'm showing you can be seen in our YouTube channel, the Viz Lab channel on YouTube, and we have plenty of videos, and all the videos are 20, 30, 40 minutes videos that you can browse and see all the different situations. One last slide on the technology. So we're working on vision. We are the last line in this chart, and we'll try to compare different technologies like HD lidars, multiplane lidars, and even the Kinect. I'm not going into the detail of this chart. I would just like to mention some of the strong points of vision, like, for example, the possibility of delivering, well, let me say, strong point of vision at our system, so the 3D system. So the 3D system can provide obstacle detection, terrain mapping as plugins. It's vision, so we have a lot of pixels, so the angular resolution is pretty dense. And the accuracy can be tuned to our specific needs. So we can play with the lenses and the field of view and the baseline to create a system that really fits our needs. I will begin giving then the floor to Paolo Zani, who will be giving you some more details on the configuration of the system.
Thanks everybody for attending. Our 3DV system comes in two flavors. The first is based on a Mini ITX industrial board, which also comes with a rugged enclosure for a total weight, including the camera, of 4 kilograms. We also have a smaller and lighter version based on a 3.5 inches board without a case, which weighs only 1 kilogram, including the camera. This smaller version has been specifically designed for applications where the payload weight is critical. For example, drones. All configurations provide an output rate of 10 Hz and can be powered through 12 to 24 volts DC power supply, and with a total power consumption of approximately 100 watts. The stereo camera selection impacts on the overall performance via different hardware parameters. The first is the baseline, that is the distance between cameras, which determines the accuracy of the reconstruction, the lenses, which affect the field of view, and the image resolution, that is the number of pixels. This table illustrates the available configurations along with their accuracy in the close, medium, and far range, the field of view, and the physical dimensions of the stereo camera head. All the configurations optionally come with external synchronization and a waterproof enclosure. The system output consists of UDP packets over a gigabit Ethernet connection and includes both the left and right images, possibly rectified if needed, raw 3D depth map that provides one distance estimation for each image pixel, a list of detected obstacles, and terrain mapping as a mesh, and more specifically a height grid. The base 3DV system provides a dense disparity map, while additional software plugins can be applied to provide additional functionality. More specifically, right now we have available obstacle detection in a basic version that assumes flat terrain, which is faster and cheaper, along with full 3D terrain mapping and optionally 3D terrain mapping with obstacle detection. You can see below two sample screenshots for the terrain mapping plugins on the bottom left corner and terrain mapping with obstacle detection on the bottom right corner. In the second case, you can see that the cars that are visible in the scene are currently reconstructed in 3D. On top of that, we plan to release soon a set of additional plugins which include visual odometry, pedestrian vehicle and lane detection, and path estimation. Each 3DV unit also comes with a set of additional services which can be accessed through VisLab's website. Through that, you can get firmware updates and 1-year access to our online calibration tool. This tool allows the user to easily determine the camera position and orientation once it is fixed on the target platform. In order to do so, you have to capture an image of a calibration grid with the system, upload it to the website, extract from the camera configuration the intrinsic parameters, that is the focal length and optical center, and then upload to the website the calibration grid configurations, that is its size in metric coordinates. Once this process is complete and you have submitted your data, the user can go to the next step that consists in associating each calibration grid point with the corresponding projection in the image coordinates. This can be done interactively, directly on the website, as you see in this demonstration video. You can move each marker. And the calibration tool also allows to precisely specify the world coordinates of each calibration grid marker in case the distribution is not uniform. Once you've entered all the information, you can order the system to determine a calibration, and this is the output. You can see that the extrinsic parameters have been computed, and you can upload then those parameters to the unit configuration. If you're not satisfied with the result, you can reload the calibration and more accurately determine the position of the markers on the image, such as in this case. And you can see that the calibration quality has improved. A cross-platform open source client is also provided. This client allows to interact with the 3DV unit, and more specifically, it can record data in several formats, display a live output of the unit, and it also allows to view and modify the unit configuration, such as, for example, the calibration parameters that we have determined as I just explained with the calibration tool. The client is based on lib3dv, which is an open source C++ library available from Viz Lab for free. This library provides a convenient way to communicate with the unit, allowing to access programmatically both stream data and configuration, and it only requires CMake for building and the Boost libraries. Here you can see a screenshot of the 3DV client options with all its capabilities shown. You can see that this client allows to interact with the unit both in terms of its configuration and also to perform the recording and playback. Here you have you can see a screenshot of a streamed image on the bottom left and the corresponding 3D reconstruction. Specifically, you can see in the green dots represent the terrain mesh, and the blue and yellow boxes represent the detected obstacles. In particular, the yellow group of boxes corresponds to the pedestrian, while the blue boxes correspond to the wall that can be seen in the background. Finally, we are also developing an Android application to access exactly the same data from your portable device.
Okay, now I would like to continue on and mention a little bit about the next steps of this system. So this is a chart that shows you the current system. So we have a camera. stereo camera. The camera provides data to the processing engine, and the processing engine runs the low level first, delivers the 3D representation, meaning the disparity image and the 3D point cloud. And then you have a series of plugins like terrain mapping, obstacle detection, and obstacle tracking. These can and cannot be there, so may or may not. So you may also have a system with just the low level, or just one plugin, or just two plugins. This is the current version. So we're now moving to a next version, which will be completely compatible to this one. But we are moving the low-level part into the camera. So we will have a smart camera that will be able to deliver the 3D point cloud directly to the processing engine. By doing this, we are freeing some processing time in the engine, so that we can host more plugins. So not just the 3 plugins that we have now and the ones that we are currently developing, but the very same system will be able to run other plugins. So we are trying to extend the functionality of this processing system by just moving the low level away and including that into the camera. And this is the next version that will be completely compatible to the one that we have now, but will have more features in terms of number of plugins and even the frame rate. I would just like to mention that a couple of days ago we presented our next autonomous vehicle. The name is Diva, and was officially presented here in Parma a couple of days ago. And the reason why I mentioned this is that our vehicle is really heavily based on the 3D technology. So we are integrating more than 10 3D systems into the vehicle with the aim of covering all over the vehicle in stereo. So having 360 degrees coverage around the vehicle with stereo systems. And this is a chart that shows you roughly, well, it's just an indicative way of a qualitative way of showing you the coverage of those systems that we have on the vehicle. We're taking special care about the integration of all these systems. 10 3D systems means 20 cameras, but all of them are very nicely integrated into the chassis, so they are not visible. And that's all for the presentation. I would like to give the floor back to Bobby if there are any questions. Thank you.
Okay, thank you, Alberto, very much for the presentation and presenting to the world your first commercially available product that I believe is just really the beginning of the work that you've done over the last 20 years. So thank you again for taking the time. Now we're going to open up the floor to questions. The process for having questions is please press the little hand button, and we will grab you and unmute you, and then you can openly ask your question, and Alberto or his team will answer it. So if you have any questions now, please raise your hand, and we will answer them. And we will go one at a time, so if you have your hand raised, we will get to you. The first question, we have just unmuted you, so go ahead and ask your question.
Okay, hi, I'm Adegaman from Scania in Sweden. We're a truck manufacturer, and it seems interesting. I have a couple of questions regarding availability and whether you see that this is a system for production or research. So are you able to supply thousands of units? And how about the price points for 1 unit compared to, let's say, 200?
Okay. Can you hear me? Well.
Yes.
Oh, okay. Good. So currently, we just launched the system in January this year. So we are targeting at just a few units, but the units will be manufactured here in Parma, in our headquarters. But we are also now starting we're already talking to someone that might be able to deliver more, especially when we move on to the next version. Because the current version that I just mentioned, it's based on a commercially available camera and a commercially available processing system. The next version will be almost fully custom. So the camera will be actually completely custom. We are designing our own camera with the sensor, the lenses, and the processing on top of it, and the enclosure and everything. So that will be our camera. And then the processing system, in that case, will still be acquired, so off the shelf. But we are also thinking about the next version in which we will put everything into the camera. So by just coming back to your question, now we are able to deliver a few units, few meaning, let's say, in the order of tens. But we are moving on to the next version, and the next version will be providing much more. The possibility that we have will be much wider.
Okay. Okay, thank you. Can I ask another question?
No, I don't think so.
Okay. So I was looking at the videos, and I think that the performance seems very, very good. Congratulations on that. There's one thing that I didn't see that is a little bit of a concern for us. If you're targeting an off-road site, you'll often have problems with small, sharp rocks, which will destroy your tires. These rocks are called cat skulls, so you can imagine what size they might have. Do you think that your system might be able to detect those, let's say at the range of, I don't know, 5 to 10 meters?
Okay, you mean the height will be 5 meters, and the size of the rock would be in a few tenths of centimeters, I guess.
Yeah, yeah, but I would say that the height might be around 2 meters.
Okay, well, if it's 2 meters, I don't see a lot of problems. Actually, we are actually investigating a similar system for mining, and it's not exactly the application that you mentioned. It's slightly different, but our goal is to determine the shape of a hill that we have in front of us, and that can also be very small. So a little bump or a hill. Yeah.
Yeah, yeah. So these cat skulls, they are debris left from if you have a mine and you're putting dynamite in there to break new ground. These things fly away and scatter all over the place. And if you run them over, you will most certainly break your tire, and you will have a production stop in that case.
Sure, that's a very interesting application. I would like to see images of that to fully understand if the capabilities are matched.
Yeah, okay, okay. I can see if I can dig something up.
Yeah, sure. Okay, thank you. So is there any questions?
Hello, can you hear us?
Hello.
Yes.
Go ahead.
Hi, this is Qi Wang from Caterpillar. Thanks for the good presentation. We have several questions here. The first one, we saw that the 3D reconstruction from your system is pretty smooth. So what did you do to reduce the 3D reconstruction noise? Hello?
Yes. It really depends on what you mean with 3D reconstruction noise. We are, as I mentioned, the very first part is the disparity image.
Yeah.
But it's not the SGM, the usual SGM algorithm, so we are putting additional filters to that. And that delivers the 3D point cloud, which is quite smooth already. But the important point is the second step, which is the labeling of every single pixel. So, and that, as I mentioned, is very tricky. really tricky because it really depends on the kind of obstacles that you are facing and the definition of obstacle. And once you have that, if you are able to isolate the terrain points, then you can have a very smooth representation of the ground. So I'm thinking about you're referring to that. Am I right?
Okay. Yeah. Thank you for your answer. Another question is that does your processing engine work with third-party cameras?
Well, could be possible. We need to understand what, because our system currently gets 2 images. The 2 images needs to be synchronized, needs to be calibrated, and if you have a camera which has synchronization signal, so the 2 images are synchronized, and you have a nice calibration of the 2 cameras, and you're able to keep the calibration, I don't see much issues in this. So you would be able to plug into our system. It depends, for example, also on the protocol. So if it's FireWire, if it's Ethernet, so it really depends. So there might be some more work to adapt to the protocol, but in principle, in theory, I don't see any issue with that.
So what's the current interface between your camera and your processing engine?
It's FireWire.
Okay, I see.
Yeah.
But in the next step, so for the next version of your system, it's going to be what kind of interface are you going to use?
Yeah, we are going to use Ethernet for that. So the camera that we are designing now will be able to output Ethernet and CAN messages, but we are thinking that Ethernet would be a little better because of the bandwidth, but we're still considering also CAN as a viable possibility for output of some smaller amount of data.
Okay, thank you. So it's interesting to see you put like more than 10 cameras on the car. So I'm wondering, like, does each camera have a unique processing engine, or does like one engine handles several cameras?
Yes, actually there are more than 20 cameras, so not 10. And every single 3DV system is composed of a stereo camera and a processing engine. So now on this car we are using the current version of the 3DV. But in a future prototype, we might be using the second version, but not now. So now we have the first version and we are using it.
Okay, thank you. And my last question: so, what is your plan for in the future to deal with a night stereo vision?
Yeah, we have seen that we really need illumination. We have been testing also infrared, near infrared and far infrared, but as long as you have a well illuminated area, you are okay. So in the video clip that I just showed you, the illumination was really poor. But nevertheless, you could detect the object because they were illuminated. They had headlights. So what you are thinking about that is put headlights on the vehicle.
Any other questions?
Thank you. So any other questions here?
Thank you. So
okay.
Back to Bobby. Bobby's, it's for you.
Yeah, we have just unmuted the next question, or the next attendee who has a question. His last name is Labani. Please go ahead with your question. Okay, we're going to go ahead and move over to the next one, which is James Welling. Go ahead, James.
Hi, very good afternoon, and a fabulous presentation. Just a few questions related to the fabled Google car. how do you folks compare yourselves with Google Car? Do you feel you're ahead of development? And also, what's your Google Car? I'm sorry. Whoops. Your technology, is it? Do you reckon it'd be retrofitted to existing cars as a product, or do you think you'll link with a car manufacturer to launch your product? Thank you.
Okay, well, thank you for the question. Well, yes, the Google car is an example of a different technology. Many other research centers are following Google's approach based on a very detailed map of the surrounding and using this very high, quite expensive sensor, which is on top of the roof of the car. It's a 3D lidar, which delivers a very dense quantity of information, very, very precise and very generous technology. We are not using that because, for mainly two reasons. Because the first reason is that it's quite expensive now. It's really much more expensive than the car itself. But the second reason is that it really needs to be mounted on top of the car. So even if the cost would be lowering, maybe 2 orders of magnitude may be reasonable in the future, but still you need to put that on top of the vehicle or on the bumpers if you have many of those. And the bumper position is usually some position which will be hit sooner or later. So you don't want to put too much technology in that position. So what we are doing is that we are trying to focus on a completely different approach. So being more reactive to the world rather than localizing ourselves into a map, predefined map. So Google's and others are using this approach of having a map, detailed map. We are using more reactive behavior. So we are trying to perceive the environment and react on the basis of that. So it's more difficult in our case because you need to be able to handle more situations, but then you don't need a map. And a very detailed map means big data, and if it's very detailed, it also means that you need to have very frequent updates. And this is something that we will never be able to do. I mean, Google is able to do that because they demonstrated to be able to do that. We would not be able to do that. So we are focusing on a very alternative way of reaching the autonomous driving.
Just to follow up, if you don't mind.
Sure.
Sorry. Basically, I'm disabled and unable to drive, so technology means a hell of a lot to me. You wouldn't know. I've been thinking the last couple of weeks about having it introduced in stages. Like, I know robo-tax has been thrown around. The industry's thinking a lot. Would it be possible to use your technology on, say, motorways? Say, if I wanted to go, I don't know, from London to Scotland or on a particular motorway, can I get in a robo-taxi with your technology and do that route fully autonomously? And if so, when?
Well, actually, you are touching two different topics. So the first one is perception, which is actually the main topic of today. And the second topic is navigation, so understanding the environment and moving into the environment. This is a topic that we didn't cover today, and it involves many different considerations. So it's not just the perception, but also the possibility of knowing, of having a map, of being able to move into this map, even legal problems are considered in this case. So I would just mention the perception part in my question, in my answer. And perception-wise, what we are trying to do now is that we would like to reach the same level of perception like the great sensor that I just mentioned, the laser, but without the laser, with just vision. So we are trying to solve autonomous driving perception using cameras. And what we did last year in July is that we traveled downtown Parma, and we were able to handle everything. So all the roundabouts, all the pedestrian crossings, traffic signals, and so on. without any human intervention. We did that last year with a simpler version of the vehicle that we presented yesterday.
So in a application, how would that help me? Because I know obviously people who drive at the moment, e-technology help them, but do you see this helping me?
Well, definitely we are working for that, but not tomorrow. I'm seeing...
Oh yeah, yeah. I knew it'd take a few years.
Yeah, definitely, definitely. That's exactly the reason for our work.
Before 2025?
Well, someone says 2020. Some car makers are saying 2020, and I'm sure that 2020 will be able. Yep.
That's semi-autonomous. I've got a thing about a car manufacturer saying, oh, they're going to do fully autonomous. Sorry, they're going to say autonomous. They're only doing partially autonomous by 2020, not fully autonomous.
Maybe fully autonomous in some specific situations, like highway, like specific lanes, so some specific areas in the world. Yeah.
I'll leave you in peace. I know there's a one-day conference coming up in the United Kingdom at Nottingham University, so I'm hoping you'll be coming to that. But if not, thank you very much.
Thank you. Thank you so much.
Okay, we have a few questions that have come in from people who do not have microphones. So I will ask the question on their behalf. One question is about the video streams and the data going over CAN bus. Their concern would be that CAN bus may be a little slow, and can you address that question and how you handle the bandwidth and streaming all the video and data over that bus?
Yeah, sure. Well, currently we are using Ethernet. In the next version, we will be using Ethernet. So the CAN bus will be used to issue not just to broadcast not just the images, but some other data. So if you do some processing in real time on the camera, then you will be able to send those partial results through the CAN bus. So you don't really need a lot of bandwidth to do that. But you do need bandwidth if you want to broadcast images. And I mean, you're right, the bandwidth may be too small to fit 2 images in real time. But now we're using Ethernet.
Okay, thank you for the clarification. The next question is about reliability concerns. This individual had spent some time with you on the Parma-Shanghai trip, and some things had come up, and they were wondering what has been done on your end to increase reliability.
Reliability, what does that mean? I mean, I'm seeing that from the perception point of view. And from the perception point of view, I mean that the system now is more stable, meaning that it can handle more situations than what was handled in 2010, because we have been improving the system. I'm not talking about reliability regarding the hardware failures, because this is another topic. So today we're addressing the perception problem, and what I can say is that our system now is much better than the one that we have in 2010. So it's more reliable from the perception point of view. Actually, we recorded all the data in that trip, and we have so many gigabytes of data on our servers, and we have been going through this data again and again and again, and have been focusing on the most difficult situation where the system didn't work, and now the system is working much better than that.
Okay, thank you again. The next question is in regards to system security. So if you have this on the road in mass production, is there a way, or have you thought about the defense mechanism against someone spoofing the objects that are being detected by the stereo camera?
Okay, so you mean hacking into the system and changing the firmware and changing the behavior? No, actually, there are a few items that needs to be considered when you move to the product. We have been focusing on some of those. We haven't been focusing on others. So we are now focusing on low cost and integration. We are not focusing on redundancy, not focusing on security like hacking that you mentioned. So these are issues that someone else will be focusing on that, or maybe even us will be focusing on that at the second stage. So currently we are targeting our research and our efforts into having a system which has a low cost, has a possibility of a straightforward integration in the car, but as long as redundancy is concerned, no, now we're not redundant. So we only have one system. If that system breaks, you're on your own. So you have to have, for example, two systems like this, or different technology. So in our car, we have vision and we have lasers. And the two results are fused together. And if there's a fault in one of them, the other should be able to detect that.
Okay, I'm going to turn it back to the attendees. We have another question from Isaac. I'm going to go ahead and unmute you now.
Yes, thank you. I was just wondering if you guys have experimented with a number of baseline. Does this system comes with a different baseline to support various type of ranges, or it's for now it's fixed? And if it's fixed, what's the current spacing between cameras?
Yes, we have different versions. Actually, Paolo mentioned that. Currently, we have two versions, 12 centimeters and 24 centimeters. But we have been experimenting also other systems. We have a 12 centimeters baseline system here in the lab. Even very, very large baselines, like 1 meter baseline, for a totally different application. But we did that. And I should also mention that we have an online calibration system. And it's a demo that we have here, which is running 24/7. And it's used when you have two cameras mounted on a system, and the two cameras are not fixed on a rigid bar. In that case, maybe that one of the camera moves and it gets misaligned with the other one, and the system is able to pick the calibration, the original calibration, back in just less than 1 second. So if you have your stereo system, you move one camera, the system goes blind for less than a second, and then it picks it back. So this is something that we have in our laboratory, but it's not available on the 3DV system now.
What kind of performance like when you increase the baseline? Would it drop significantly, or stay good enough for obstacle detection, for example?
Well, when you change the baseline, you just change the capacity or the capability of the system in addressing obstacles far or close. So if you have a large baseline, you will lose the possibility of detecting close obstacles, only far away obstacles. If you have a small baseline, it's the other way around. So it's just a matter of refocusing your system. So if you have a specific application, you will then need to specify your baseline and then live with that.
Okay, thank you.
Thank you.
Okay, the next question is coming from Andrew Klofas. We will unmute you now.
Thanks. Can you talk about some of the capabilities with respect to visual odometry?
Actually, no, because we are still developing that. We have a first version now, but it's not available now for the 3DV system. That will be one of the first plugins that will be included. It's visual odometry and detection of vehicles, lane, and pedestrians. That will be other plugins that will be added soon. But no, currently I cannot say anything about visual odometry because it's not there. I'm sorry about that.
Okay, thank you.
Okay, Alberto, I'm just checking to see if there's any other questions that have been sent in. I think the ones that are left will probably address afterwards. Well, here's one. Back to the spoofing question. The question is more related to like a fake object on the road, like a laser pen on the camera or something like that. Have you done any work in trying to determine when someone is trying to cause problems like this?
Oh, I understand now. Okay. Well, that's very tricky because if if you paint a line, if you erase the lane markings and you paint a line which goes into a cliff, then the vehicle will be following that. So if you are able to provide an object, a foam object with the shape of a car, that would be detected as a car. So it's based on vision. So no, I mean if the visual aspect of the object is very similar to an obstacle, well then it would be detected as an obstacle. So yeah, it suffers from the same problems of vision. This is why actually I was mentioning that you should have two different technologies on the vehicle, because if one fails, then the other one may be able to get the correct measurement.
Okay, another question, which is kind of combined from a couple of questions, is have you done any work yourself, and do you have a service or a product available when you're fusing other technologies with your stereocam data, like lidar or other camera data or radars?
Yes, we have. We developed that because we have in our vehicle, and for example, the Brave vehicle that we used last July, we had lasers and vision, and we had fusion of them. Even on the vehicles that travel to Shanghai, we have different technologies. In the new vehicle, we have different technologies. So we do have fusion, but it's not a product. So what we decided to do now is just to try to commercialize some of the technologies that have a high potential and have reached a level of maturity which allows us to sell them. And the first thing is the low-level perception with vision. So that's already, I mean, we are very satisfied by the results that we got. So we are now selling that and try to have all the people work on this and use this to boost their possibility of reaching autonomous driving faster. But we do have fusion boxes, but I don't think they reach the same level of maturity to be able to be sold as a general product. For example, if you have a specific application, we might want to customize the system that we have and address your single problems with our specific solution, not as a general solution. This is not available now.
Okay, we have, looks like one more question from an attendee named Aina. I'm sorry, I may be butchering your name, but Aina, we're unmuting you right now.
Okay. This is Ina from General Motors. So my question is it so is 3D reconstruction is rich enough that you can really to get a good 3D reconstruction of a road boundary? I mean curbs. So is the accuracy of a 3D reconstruction sufficient for that?
So I'm sorry, I didn't think I captured the whole question. So you're thinking about the bumps on the sides of the road?
No, I don't speak about bumps. I speak about curbs.
Okay. Yeah, sure. Yes, it really depends. If you're interested in curbs, you might want to lower the threshold and be able to get those. I'm not sure if you were able to see in the video that I showed that the 3D reconstruction actually was showing that there was a step there. It wasn't detected as an obstacle because we didn't want to be detected as an obstacle because we were looking for larger obstacles. But if you're concerned about that, you might be able to tweak the system and change the thresholds and be able to detect that. For example, curbs can be detected when they are close to your vehicle. It's not that important to get a curb at 80 meters from you. So you might be able to, fine-tune the system to be able to, and then sensible to curves in the close range and not in the far range. So there's a number of thresholds and tweaks that you can do to detect them. Yeah, yes, they can be detectable.
And another question is, if we speak about like road profile that is extracted from the road surface, so how accurate is it for the range of 20 meters? So if I'm looking for the bump, so if I'm interested in the bump and the bump is of a height of 4 centimeters, so what is the accuracy of the system in 3D reconstruction?
So 4 centimeters, it's too small. I am not sure you will be able to get 4 centimeters with this sensor at a distance. You might be able to get that when you are looking very, very close, but not at 20 meters. That's too small.
So do you have some plots that show the accuracy as a function of a distance from the camera?
Yes, I think Paolo mentioned that and in one of the slides, but if you want, I can also send you some information on that. There was a slide that Paolo mentioned, and there's an accuracy that you can reach at given distances based on the system. So we have 6 different versions, configurations of the system, and each of them can reach a different accuracy at small, short, medium, and long range. So you will be, for example, be able to get, I don't remember, it was a few centimeters at a couple of meters. So I think it was 1 centimeter in 2 meters, maybe in 10 meters you can get up to a dozen centimeters. But these are just qualitative numbers. If you want, I can find them currently. Maybe I can ask Paolo to find the correct slide. Okay, so the correct slide is this. With the one of the configurations, or the first one, you can reach an accuracy of 1 centimeter at 1.8 meters. That means...
Okay, thank you very much.
Yeah, okay, good. Thank you.
Thank you.
Okay, Alberto, we do have another question that came up. This one is from Stefani. So we will go ahead and unmute you now.
Yes, hi. This is Stéphane Francois from Cogniview in Canada. I have a question. I've seen in your slide that I imagine that this is for your current version, that you have the performance of 10 frames per second and the power consumption of 100 watts. And I was curious about what was your target for your new generation.
Yes, the target for the new generation is actually we are almost there. It's 30 frames per second on the camera and 2 watts for the camera. Then you will need the processing, the plugins. But again, as I mentioned, we are now working to move the low-level part into the camera, and that will be the numbers that I just mentioned. So 30 frames per second, we are almost there, and 2 watts for that.
Could you indicate what kind of technology you used for?
Yeah, it's an FPGA. It's a system on chip within FPGA. Yeah.
Okay, so that sounds like.
That's the next version. So we are now focusing on the current one.
Okay, I see. Okay, thank you.
Thank you.
Alberto, we do have a couple more that have come in. I will say that we probably will only take about 5 more minutes of questions, and then if you have any other questions, you can just email them to me on the address on the screen here at rhambrick@AutonomouStuff. The next question is regard to terrain mapping and obstacle detection. I'm just going to read it here. Is it only based on the frame point cloud that is captured at the moment, or do you fuse the new data with the old data?
Well, regarding terrain mapping, you're right. It's on a frame-by-frame basis currently. So the version that it's on the 3DB, it's on a frame-by-frame basis, but obstacles are tracked. So we are tracking obstacles. So that's the current version.
Okay, great. And that answers the next part of his question. So thank you for that. And for everyone else on the line, we are recording the session, so we will provide a link following this with the entire recorded webinar. And if you have any other questions, you can just send me an email directly, and I can help answer those. Okay, I think that's it as far as I can tell. Alberto, do you have any other closing statements before we move on?
No, actually, I would like to thank you all for attending. Actually, we are, as I mentioned, we are very happy to be able to move to the next step. So instead of just doing research and providing this technology to our vehicles, we would really like to provide this technology to the whole community, so that the whole community can just forget about the low-level part and focus on the high-level part for autonomous driving. So forget about disparity engine, forget about the point cloud, and really focus on navigation issues and on planning issues, so the high-level part. Thank you so much.
And thank you again, Alberto, for doing all this research over the last 20 years and being kind enough to share it with the world. And we're very excited about that. I would also like to reiterate that we do have a special deal for the next 30 days after this. So if you're interested in the technology or you need additional information, we'll be happy to set up an individual meetings for each and every one of you. And in the meantime, yeah, we're looking forward to our next steps together.
Thank you very much again.
All right, thanks everyone, and we're closing the meeting.
Thank you.